Hello. Let's finish up this conjugated chapter. So we need to talk about how it affects light. And before I can do that, we're going to finish up this section called the molecular orbital perspective. All right, I'm going to look to the whiteboard, but I'm going to give you some definitions here. So HOMO stands for the highest occupied molecular orbital, where LUMO stands for the lowest unoccupied molecular. Now, if you were going into chemistry or going into research, it would be very important to understand the nuts and bolts of the molecular orbitals. I'm going to give it to you again in the visual representation, just so that you can understand why some of these reactions are happening. All right, so molecular orbital theory. Let's go back to Gen Chem. A long time ago, we talked about combining atomic orbitals into something called molecular orbitals. Make it as close as I can to what we did in the past. And then we lined up these, and we'll just start with the twos. I won't do underneath. So the two S's, two P's, and then don't forget the one S's also in the back. All right, when you take these atomic orbitals, they are converted into two molecular orbitals. One has a higher energy and one has a lower energy. So this is called the anti-bonding orbital. The lower energy one is called the bonding orbital. And then, of course, we put names with it. So this one came from 2s, so we called it the sigma 2s. This one also came from the 2s, so it's anti-bonding, so we call it sigma 2, so that's a 2s, and then the little asterisk for anti-bonding. And then the electrons would go in. Well, the same thing will happen with these p orbitals. Now, generically, we put one lower, two higher, and then two, and then one. And we call this the sigma 2p. Well, that's not a 2 in P. Sigma 2p antibonding. And this one we called the pi 2p antibonding. And the pi 2p antibonding. And this one was the sigma 2p bonding. This one is the pi 2p. The pi 2p. All right, that's what we did in the past. And we went, oh, hey, can we tell anything? All we really got out of it was the bond order and whether it was magnetic or not. But we're going to use the pi systems now. I'm not so interested in the sigma bonds, but I'm going to use those pi's. So we then would put our electrons in our atomics. And those would have to come together. So let's take a look at what's happening down here at those two sigmas. Okay. In order to bond, that is a S, and this one is an S. You can either have a good combination or they can come together, I guess for want of a better word, in a bad combination. Okay, so that's called a node. Okay, so it's higher in energy. So you can have this nice bonding. You can have this antibonding. Those are your only two possibilities. Because if I didn't shade them both, you go back to just this good possibility. And the terms good and bad aren't quite descriptive enough. Well, the same thing will happen when you bring p orbitals together. So, the p orbital. All right, so what are my possibilities? I could form a good possibility or a not so good possibility. And again, that would be my pi and my pi antibonding. Now that's only one p orbital, right? Or sorry, not one p orbital, one pi bond with only 2 electrons. What happens when you start combining more of them? So for instance, I've drawn 1, 2, 3, 4. So this is carbon and this is carbon. And then we would have filled these up. Okay, so that one would have been full, wouldn't have helped us much. If you'll notice, there are electrons in 2 of the pi orbitals. This is where we're actually going to explain that. Now, again, if you'll just stick with me, okay? It's not like you have to be perfect at this, but I need you to understand where it's coming from. When I need to make these conjugated systems, I'm only interested in the p orbitals, so I'm not going to worry about these sigmas, okay? But I have to know what kind of possibilities I have. Let me erase this. And so my first possibility is I could have a pi and an antibonding pi, okay? And that has a delta E. And it's pretty big. That delta E is pretty big. Energy increases like that. All right, so that's one double bond. Well, what pictures is making that up? Okay, so just like I had before, let me decide if I should put this one. That's what those two. Well, what happens if I have more than one double bond? Well, I'm now going to have, I'm going to draw the pictures first and then the lines. All right, so I have, I'm going to put carbon so that you can see, makes it easier for me to draw. Everybody has a p orbital. All right, so statistically, the best case scenario is that one. Next would be that combination, and that gives me a node. Now next, give me which direction. The middle ones. Last but not least, the worst combination. Now, this is telling us the effective overlap, okay, or how much it's overlapping. Oh, those all are very unique, and they will have one line drawn each of them. So this one would be called pi. This one would be called pi 2. This one would be called pi 3 anti-bonding. And this one would be called pi 4 anti-bonding. And just to make things very difficult, we actually use the letter psi when we're discussing things instead of pi. I know it's one of those things, why can't we stick with one way? So whichever one you use is absolutely fine. The key is here is that delta E, and it is smaller Okay, it is smaller than in non-conjugated systems. So this is 2 double bonds that are conjugated. Oh, okay. If I had more, the gap would get even smaller. So the more conjugation, the smaller the delta E. And you're thinking, okay, thank you. That's very interesting, but why do I care? Because we're going to start talking about light. Most organic molecules have no color because we can't see it. Okay, they're still absorbing light. It just happens to be in the UV spectra. So why are some organics, not very many, but why are some organics colored when others aren't? And it's all about the conjugation. So if you have a highly conjugated system, this delta E is getting smaller. And so when you excite electrons, and so, you know what? I'm just going to drop back here for simplicity's sake. I can go there. I can hit it with light. And I can make it into an excited state. Keep one in the bottom and one in the top. So this one is stable, this one is excited. This electron wants to fall back down and it will release the same amount of energy that it absorbed. Oh, am I going to be able to see that? And the answer is no, unless it occurs in the visible region. And the visible has small delta E's. So the more conjugation, the smaller the energy difference. And now we can start to see these molecules. One last thing before I go on though, is now that you've seen the molecular orbitals, maybe when I'm drawing these this way, it might make more sense now. So here I had my diene, and here I had my dienophile, and I'm doing the exact same thing. When those come in contact, ideally, I would have a perfect alignment, and that's where those 2 new sigma bonds are formed. And that's the visual using molecular orbital theory. Interesting. All right, back to the notes. All right, so where in the world do these words come from? So the highest occupied molecular orbital, those would be the bonding. And these would be the antibonding. So this one would be the highest occupied. And this one would be the lowest unoccupied. Now, if you get into research and theoretical, can this be created, we can actually plug and chug numbers that would help us out. But that's just the overall idea behind the molecular orbital. And we need it for visibility. All right, I did a whole bunch of problems there for those girls out there. All right, so our conjugated dienes and light. Let's do a little review on what light is. I guess technically it's not a review because it was a long time ago and we didn't really focus on it. But when you see something, you're not seeing the color that's absorbed. You're seeing the colors that are left over. So if this one is absorbed, so if the orange spectra area is absorbed, you will see blue, the complementary color. Right? So if you absorb in the violet, you're going to see the yellow. Okay, just as a reminder. All right, so our visible wavelengths I wrote them out there for you. So the indigo and violet is getting really close to the UV, and then we've got our blue, green, yellow, orange, red. Well, organic molecules generally absorb light in the UV region, which is somewhere between 200 and 400 nanometers, and we can't see that. Now, do we have equipment that can see it? Well, yes, but not our eyeballs. All right. As the number of the conjugated pi bonds increase, that energy gap gets smaller between the ground state and the excited state, and it will start to shift to absorb into the visible region. So keep in mind, if it absorbs right here, the color you would see would be the yellow. And that's why we don't have horribly interesting organic molecules with lots of color, but we have lots of deep reds, oranges, yellow, because where are they going to start to absorb? They're going to absorb in this violet and blue area. So there's our organics, which are conjugated. Well, how many bonds do we have to have? Generally, 8 or more, if you want to get into the region where you can see them. And again, you'll probably see from red, reddy orange to yellow. Those are the colors that we would see most often. So remember, the color that is seen is the portion of the spectrum that's not absorbed. Well, how do these molecules do that? Okay, we're not going to draw the whole molecular orbital thing out, but we are going to talk about something called a chromophore. That's just the area or the portion of the molecule that actually absorbs the light. And there are some naturally occurring ones. And so there's some terpenoids, carotene and lycopene. This one's carrots. This one's tomatoes. Okay. And I lumped them just both together under terpenoid. And then there's the quinones. And the one that we really appreciate is something called melanin. There's porphyrins, which are surrounded by rings, and hemoglobin and chlorophyll. There's lots of them, but these are the ones I thought you'd recognize. The anthocyanins, these are these really deep pigments, like in red cabbage and huckleberries and the deep blue and blueberries. Okay, so those are those dark pigments. And then the ones that we have used in lab, you probably don't even remember from last semester, but we made something called the azo dye, and it came out thick, chunky yellow and thick, chunky orange. Those dyes use nitrogens or azo compounds, and we can use those as tests in the laboratory. So let me just show you a picture of what we're talking about here. So for instance, here's a picture of lycopene. All right, lycopene, the ones in red right here, and of course, I got this off the web from Master Organic Chemistry website. So the ones in red are the ones that are conjugated. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Ooh, so that's highly conjugated. So we expect it to be seen, and we see it as red. We see it as red. Well, carotene has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, also 11. But do you notice they're in a little bit different conformation? This one comes out as orange, right? And then this nice yellow down here has a couple of hydroxy groups on it. But those are just some examples of naturally occurring ones. Well, those, basically, your terpenoids. What about your quinones? A quinone is generically that. It's a 6-member ring with 2 carbonyls, and it's conjugated. The quinones are, melanin. So let's find, so this one happens to be melanin here at the bottom. Are you seeing that moiety right there? But the most important thing is, can you see how conjugated this system is? Again, I like to draw my little p orbitals. That helps me see them better. Whoa, that entire ring is conjugated. Oh, so is that one. Oh, so is this one. This is the reason that it can absorb the extra energy and try and avoid sunburns. Okay? But it happens to be that quinone area that kind of gives its functionality. All right, I didn't draw anything for the anthocyanins, but I did find a molecule that will show you those porphyrins. So the porphyrin is this outside structure, and it's alternating, 5-membered rings with attachments, but it has nitrogens in a ring around usually a metal. Whoa, there's some interesting colors in nature. So chlorophyll uses magnesium, and it happens to be green. But our blood uses iron, and it happens to be red. But if you'll notice, both of those metals are surrounded by that porphyrin ring. If you change the attachments on the outside, you can actually change the colors of the rings. So like put a whole bunch of chlorines on them or something like that. But you can play with those and make different colors. All right, let's see. Here is just a few examples. Oh, quinones again. So here's that nice quinone function. So this one is alizarin, very bright yellow. Okay. This one is harmonic red. If you'll notice, there's lots of O2H's, there's some hydroxys. Ah, that probably does something with radicals, yes. But as far as color is going, if I started drawing my p orbitals in there, these are highly conjugated systems. And we're not limited to just carbon and oxygen, of course. You can have nitrogens in there as well. So if you wanted indigo, those Z groups would be hydrogens. And if you want nice purple, you can put some bromines on it. Okay. And the saffron has 1, 2, 3, 4, 5, 6, 7, 8, and 9. Well, what wavelengths are we actually talking about? Again, you are not going to memorize these numbers, but I'm just going to give you a visual. Go back to my whiteboard. Okay. So if you just have a carbon-carbon bond, if you just had a carbon-carbon bond, that would show up about 170 nanometers. And we have to jump over the answer key to get my numbers. All right, so the carbon-carbon. Well, what if I do 2? Well, let's do a cyclic. Okay, so it's still 2. It just happens to be in a ring. What about 3? And then let's get really wild and crazy. 1, 2, 3. One, 2, 3, 4, 5. Let's put 1. Let's put 6. Okay, we're clear down in the 170 nanometers, and often that was written as round max, okay, where it's absorbing. So that's not going to be visible to us. Well, this one is not going to be visible to us either. And I'm going to pause and go get my. All right, let's see if that works. I had it on scan. I couldn't find it. All right, so those numbers are 317. This one is 256. 3 in a row is around 260. And this giganto thing is like 364 nanometers. So it's a significant difference that is going into the visible region. So highly conjugated. It makes the delta E smaller. So it starts to absorb in the visible region. Now, when we were in inorganic chemistry, we talked about fireworks and how we got those colors. Remember those, the inorganics, were playing with the d orbitals. And that gap is much different than the one that we are talking about here. So we don't get all the wonderful colors like fireworks, but it's the same idea as the gap, jumping between the stable state and the excited state. All right. Well, I mentioned melanin. Let's just talk about sunscreen to tie this up. If you wanted to absorb that extra energy and so it didn't go and mutate your cells, what would you use to absorb it? And the answer is conjugated systems. And so this one is very common. Called para-amino benzoic acid. So para-amino benzoic acid. PABA. And then another synthesized one. Just has a variation on a theme. It has 2 methyls on my nitrogen. And now I have an ester group. And 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. This one is called so both of those work in a sunscreen system, and you are absorbing with these conjugated areas. Now the key is, how do you get one that will stay on when you want it to stay on, or wash off when you want it to wash off? Now that's where, well, science becomes also an art, but that's the idea behind our sunscreens. We'll jump back over to the notes, make sure I cover everything I wanted to. Let's see. All right. I think that's going to tie together all of our conjugated systems. Just as a review of conjugated systems. All right, everybody has to have a p orbital, which means we have delocalized pi electrons. How are we going to use those in our reactions? If you look on your reference sheet, I have one area underneath the alkenes called conjugated alkenes. You saw 1,2 addition, 1,4 addition, and the deal's over. Now, the reason there aren't very many of them is we're going to be talking about benzene in just a little bit, and that has lots of variety. So our conjugate systems, exceptionally stable, but they can react. We can control some of those with temperature. And of course, the Diels-Alder requires a little oomph to get it going. And that takes care of basic conjugated systems. All right, until next time, shall we out.